This is lesson 6.5, and as we look into applications of integrals, today we will try to find the volumes of solids with known cross-sections. And you're like, what does that mean? So think about how we find volume. Maybe think back to grade 8 when you looked at volume of a rectangular prism. Don't write this down, but what did you actually do? Well, you created the base. Maybe it was a rectangle like this. And then to create volume, what did you do? You actually stacked layers of it, or you made a third dimension, and you created then the 3D shape. Now, you can think of this like a square loaf of bread or Texas toast. And if you think about each one of these pieces here as a slice of bread, and if I put multiple slices of bread together back to back, you can see I'm going to create my 3D object or volume. So this is kind of what we want to do today. Calculus here allows us to find volumes of solids whose bases are two-dimensional regions, like that part in blue, within an XY coordinate system. And then heights are formed by cross sections. So think, you can write this down if you want, slices of bread. And these cross sections can be different shapes, but most often we'll be looking at squares, rectangles, semicircles, or triangles. And the idea is they essentially stick out from the base to form the third dimension of the object. So to hopefully let you see this a little bit better, let me just go ahead and find some things on the internet for you to take a look at. Let's not do that one first. Let's do this one. Yes. So here is our two-dimensional base. And notice what I'm doing now. I'm generating squares as cross sections, and I'm filling this two-dimensional base area to create a 3D object. And if these squares or slices of bread are thinner and thinner and thinner, you get a nice smoother and smoother 3D object. See? A two-dimensional base with these squares sticking out of the base, creating a 3D object. Here, let's do one more. This is a circular base of radius 2. This time I'm using cross sections that are not squares but isosceles triangles, and notice what 3D shape I get to create. Cool. So the key is to have a 2D base shape. And that's kind of like what we did last lesson, finding the area between curves. So let me show you one more here. See, here are my two curves on the XY plane, the one in red and the one in blue. That's the same thing here, red versus blue. Here's my 2D picture, here's my 3D picture. Notice what I can do now is if I can, if I move this around, you see, this is what we did last over here, finding the area. We would, find this little piece and add them all up, sum them all up. Notice how that also changes along the 3D shape down here. So I'm moving along. And now let me say, hey, let's make cross sections that are squares. Hello, square. And let me move this along. Let's see what happens. Ooh, see how I'm creating a 3D shape. Notice in this case I'm only using 11 squares, but if I use more and more squares, I get the actual 3D model. And with more rectangles, I get a more smoother shape. Okay. What if I didn't use squares? What if I used equilateral triangles? How would that look like? Ooh, right? And if I were to use more than 7, there we go. I fill it in, and I'm creating a 3D shape. And finally, let me show you the same thing with a semicircle now. And I can see that one semicircle going throughout. And once again, if I were to have more, you see this lovely shape. And with more and more and more, I get a nicer, smooth 3D curve. Want to see all three together? Boom. Boom. Kind of hard. Okay, so I hope you get the idea by looking at these visuals. Now let's actually do the calculus behind this idea. So the key thing that you need to do, and you should have these memorized, are to understand that we have area formulas for common cross sections. Everything seems pretty straightforward except maybe the equilateral triangle, but you should remember that that's the key root of 4 over s squared, where s stands for the side length. Okay. Now, how do we find volume then? So the key thing is to determine if the cross sections are perpendicular to the x-axis or perpendicular to the y-axis. In this example I did earlier today with this rectangular prism, notice the cross sections were perpendicular to the x-axis. So here's my x-axis, right? X-axis. So because they were perpendicular to the x-axis, the volume formula is really equal to the integral from a to b. So starting value here, a, ending value here, b. A stands for the area shape of the cross section, and that dx really is the thickness of the slice of bread here. This is like dx right there. And so I want you to understand dx is like the thickness or really the width. So if I took area, which is a two-dimensional thing, and I multiplied by thickness, or dx, or width, that makes it three-dimensional, and that's where I get volume. Now, if I ask you to do cross-sections perpendicular to the y-axis, then we have to change everything in terms of y, but the idea hopefully is the same. Still take the area of the cross-section, now it's times dy, and if we did that, then these a and b values here are also y values. Okay? So let's take a look at some examples to hopefully solidify these concepts for you. Let's look at number 1. Find the volume of the solid whose base is a triangle, bounded by y equals to negative 2x plus 2, x equals 0, y equals 0, and whose cross sections are squares which are perpendicular to the x-axis. Now, do you see my visual that I've drawn here? I hope you can see this too. That line must be y equals negative 2x plus 2. Here's the line x equal to 0. And here's the line y equals 0. So notice that the base that I'm creating is really this triangle. And the idea is the cross sections that are perpendicular to the x-axis. So think of the slices of bread coming out of the page. Here would be one particular slice, right? Here's another particular slice. Here's a third particular slice, and a whole bunch of more slices. So these slices that are coming out of the page are squares. So, because they are perpendicular to the x-axis, I set up my volume equation as the integral of a to b of area times dx. Now, the area of each of these cross sections are squares, so the formula for the area of a square is s squared. Now, why did I choose 0 and 1 as my limits for the integral? Notice I'm starting at x equal to 0, and I'm ending here at x equal to 1. So as I put my slices of bread in this rectangle, notice I start at 0 and end at 1. The hardest part of all these questions is really to identify what the s will be. S in this case is the side length of one of these square cross sections. So the key here is to figure out what formula or what expression in terms of x, because we're talking about dx, represents the side of the square. Hopefully you can see that the side of the square is really just this distance, and that distance is really the height of y, and the value of y is given by this lovely function. So I can rewrite this as the integral from 0 to 1 of negative 2x plus 2, because that's the side, all squared dx. And then your goal is just to find the answer. So I can anti-differentiate this, but before I do that, let me expand out the square. How about 4x squared minus 8x plus 4 with a dx. I will then now anti-differentiate, so that's x cubed over 3 with a 4 in front, minus, I believe, 4x squared plus 4x, and this entire expression is evaluated from x equal to 1 to x equals to 0. And if you do this, let's see, 4/3 minus 4 plus 4. I think that's just equal to 4/3. So the volume of this solid, which is really a whole bunch of squares coming out of the page, is equal to 4/3. Okay? Now, I hope we understand this process of anti-differentiation and evaluating the definite integral. So for the remaining questions, all I'm going to ask you to do is just set up the integral. And you don't need to actually integrate it, because I just want you to see if you understand the concept of setting things up. I hope by now you can find the definite integral yourself. So looking at example number 2, I'm asking you to set it up. Find the volume of a solid with the same base as example 1. Okay, so I'm going to erase this now with the same base, that same triangle, but this time whose cross sections are semicircles perpendicular to the x-axis. So the idea is the same, just like before. I've got these pieces or slices of bread, but this time the slices of bread are not squares, they are semicircles. So imagine having a semicircle kind of coming out of the page. Okay, another semicircle coming out of the page. Okay. Now, once again, the volume formula is the integral from 0 to 1. But the formula for the semicircle is, yes, 1/2 pi r squared times dx. So in this particular example, the key thing you need to figure out is what is r? What is the radius? And if you said that the radius was equal to this y value here, I would say you are almost correct. Because that doesn't look like the radius to me. That looks like the diameter. Right? The entire y value here is the diameter. So what is the radius then? It's not the diameter of y, which is negative 2x plus 2. It's actually negative 2x plus 2 divided by, that's right, 2. So your volume formula here should be the integral from 0 to 1 of 1/2 pi. And the radius now is negative x plus 1, all squared, times dx. Alright, and once again, if you have a constant, you can always just take it out, so 1/2 pi, and just then do the integral of 0 to 1 of the function negative x plus 1, all squared dx. And then you're done. Okay, you ready for part B? So once again, same base, but this time, they are going to be rectangles of height 1/4 that are perpendicular to the y-axis. So now I'm drawing them this way. Slices of bread that are rectangles coming out of the page. And notice as I do this, I'm now integrating with respect to y. So my starting y value is down here at 0, and my ending y value up here is at 2. So from 0 to 2, and now please use dy. Once again, the key thing is to figure out the cross-sectional area formula. In this case, they are rectangles of height 1/4, which really means it's just 1/4 as the height, and timesing it by the length of the base. So the key thing for us now is what is the length of the base? And if you said the length of the base is really just this distance here, you are correct. That distance is defined as the value of x. So how can we write x in terms of y? Well, we're going to take that equation y equals to negative 2x plus 2 and really just isolate for x. Y minus 2 over negative 2. Or negative y over 2 plus 1. So ultimately now, if I wanted to find the area cross-section formula for this rectangle, it is the base, which is negative y over 2 plus 1, times the height, which in this case is just 1/4. And if you wanted to then factor out the 1/4, you can. And there you have it. This would be the setup to find the volume. Okay? Alright, you try number 3 now. Okay? Number 3, I did not draw you the picture for the base, so you might want to do that first. Okay? And I think this question combines what you learned last day too with the area between curves. So I think I'm going to be quiet for a while and at least let you try to draw the picture of the base, and if you are confident enough that you can try to find the volume, please do as well. Okay, once again, it's just the setup. You don't have to find the answer. Y equals to negative x plus 2. Sorry, negative x squared plus 2. Y equals to x. The volume of the solid whose base is bounded by those two curves. I think I need to find the intersection points. Factor, factor, factor. Okay, now we're in business. So I think this value here, the x value is negative 2. This value here, the x value is 1. Okay. So, let's start to set this up. Cross sections are squares perpendicular to the x-axis. So perpendicular to the x-axis means I know it's dx. That means I'm going to start at negative 2 and start drawing my slices of bread all the way to 1. And the key thing now is that the cross sections are squares that are perpendicular, so the formula is s squared. But what is the actual value of s in this case? Did you see that s seems to be the difference between the two y values, just like how we did the area between the curve? So remember, it's like the idea of top function minus bottom function. So in this case, the top function is my negative x squared plus 2. I'm going to minus that, my bottom function, which is just x, and that represents the side length. So this is the side length, and because it's a square, I better square it. Okay? Understanding once again, this is the top part, top function, and then minus the bottom function. See? Using stuff from last day. Alright, if you got that, give yourself a pat on the back. Yay! One more example. Next page. Okay, here once again, setting up the integral. Here I've got a solid whose base is a circle with radius 1. And this time the cross sections are equilateral triangles that are perpendicular to the y-axis. So in part A, imagine here's one of my slices of bread, and if you view the cross section, you'll see that it's a triangle coming out of the page. So once again, volume equals to, and in this particular example, because it's perpendicular to the y-axis, my integral will be respect to dy. Notice that I start down here at -1 and end up there at -1, so -1 to 1. And now the cross section is an equilateral triangle. Do you remember the formula for that? Look back at the previous page if you don't. I believe it's just √3/4 times s squared. And once again, the question is, what is s? What is the side length of this equilateral triangle? And if you said, isn't it just this? Yeah, you're right. So how do I describe that? Well, remember this from the y-axis to that point here, that's x, right? So this distance would be double of that distance. So really the side length here, the side length is equivalent to 2x, 2x's. So because I'm integrating with respect to dy, I better than be able to solve for x. So taking the equation of the circle, I will solve for x squared. Right? X is actually plus or minus, right? This would be the positive part, right? Positive part. This would be the negative part over here, and the difference would be 2x. So really, it's just 2 times the square root of 1 minus y squared. So ultimately, I should replace my s here with the side length of 2 √1 minus y squared, all squared. And if I do some simplification, then this is -1 to 1. 2 squared is 4 multiplied by √3/4. That just gives me √3 as my constant that I can take outside. And then I'm just left with 1 minus y squared dy. And there you have it. Okay. The last one I leave for you, because I think I've done enough for you. Rectangles whose heights are 3 times their bases and whose bases are perpendicular to the y-axis. So the diagram is the same. The slices of bread are the same. The only difference now is that they are rectangles, and it says the height is 3 times the base. Why don't I leave this for you to try? I will be quiet now. You press pause, you try it, then come back, and then press play to find the answer. Still dy, right? Perpendicular to the y-axis. The base is the same as the base of the triangle from above. So base would be 2 √1 minus y squared. Height, though, is 3 times the base. So 3 times 2 √1 minus y squared. And if you want to simplify this, 3 times 2 is 6 times 2 is 12. √1 minus y squared times √1 minus y squared is just 1 minus y squared. Ta-da! That's it. You're done.